So this is my cracked engineer's guide to chunking. Now, I've been working with LLM since GPT-3 came out. I've been with this journey with AI since the very start. I've made every single mistake, and this is my guide. This is basically what you have to see, and then you could kind of worry about chunking a little less for the rest of your life. So choosing a chunking strategy can be really intimidating. We have all these different chunking strategies. We have fixed size chunking, structured based chunking, semantic chunking. We have agentic chunking. We have all these different things like late chunking, contextual chunking. There's so many things to think of. So sometimes this can be very intimidating, and it's very challenging to figure out, okay, I just need to break this up into sections. What's the best way to do that so I can get some answers that aren't wrong from my LLM? Well, let's start with the simplest way we could possibly chunk documents first. Fixed size chunking. You decide, okay, I want something to be X tokens in length or X characters in length, and then I'm going to split by that length. Well, it turns out this is really bad. So here we have a visualization by ChunkViz, which is a cool app which lets you try different chunking strategies. And what we see here is that with fixed size chunking, we're breaking things up in the middle of sentences. It just doesn't give us cohesive chunks at all. It's really easy, it's really fast, but it's really bad. Well, structured-based chunking turns out to be much better. Let's say we have something like a markdown document, or maybe specific coding language, or something that has structure. Well, what we can do is we could figure out which delimiters work best, and then we could break it down, and then we can use structured-based chunking to create pretty cohesive chunks extremely quickly. So this turns out to be way better, and for something like Markdown, structured-based chunking might be a very good decision. You might not need to have a more advanced chunking strategy like semantic chunking. But there's still drawbacks to this. Sometimes for just general text, there's not that much structure you could possibly parse. Something like PDFs, you might be turning them to Markdown first and then using Markdown chunking, and that might be extremely effective. Or you might find that you're just not getting the results you need, so you might need a more advanced chunking method after that. But this is probably the best place to start. It's fast, it's easy, it's cheap. Let's move on to semantic or embedding-based chunking. Semantic chunking has one thing in common. There's lots of semantic chunking strategies. But the main idea is that I break my text up into many, many parts. I segment it into tiny little parts. And then my task is to figure out, how do I connect this into larger, more cohesive chunks or parts that make sense? Well, it turns out there's many, many ways to do this. The simplest way, and when people say semantic chunking, this is usually what they mean, is to simply check whether the semantic meaning of a following text segment or tiny segment significantly changes the meaning of, is a significant change in the meaning as measured by something like cosine similarity. So we have a vector that represents every little segment, which could be a sentence. And if that vector is very different from the previous vector, then we split at that point. So here we have a visualization. And here the breakpoint is a 0.1 difference in cosine similarity. What we can see is that we segment quite a lot. And then if we move this to 0.2, we would segment much less. So now our hardest task is to figure out, okay, what is this breakpoint that makes the most sense for a text? And we might add something like a minimum text size for a chunk. I'm so sorry, I don't know why this is happening. I know this is very annoying. Let's try this and hope this works. Please work. There we go. There we go. And we might also want to make sure that our chunks are of a minimum size. In practice, that just helps this algorithm work a little better. So semantic chunking seems really simple, but what makes it complex is that this is the most naive way to do semantic chunking, just seeing if this breakpoint happens. What you could do is you could create much more advanced algorithms that try to figure out, okay, what's the best way to combine these little segments together? And another problem with them is that embedding generation is slow, right? If we call OpenAI every time we want to generate an embedding for every single one of these tiny segments, well, we'll be here all day. And we're relying on an external service. This doesn't sound great. This doesn't sound like a great way to solve chunking, especially if you're doing chunking at scale. Let's say you're parsing 50 million, 100 million documents. That's not something you want to be doing. One solution to this embedding latency problem is very small embedding models like Model-to-Vec. Model-to-Vec was a project that distills embedding models to much smaller versions of themselves where basically you avoid much of the embedding latency, right? The quality of these embedding models, they can be fine-tuned, but generally the quality of these embedding models is slightly lower. But this is a task where general quality of embeddings isn't necessarily that important. So we could still use these small embeddings to chunk. And for some context, I remember a project, I'm not going to name what specific company, they were inserting around 40 million documents, 40 million chunks into their vector database and generating embeddings for them. And this took them several days. They had a server running. With this, I could generate 100 million embeddings in an hour or around an hour on a CPU. So it's a completely different time scale in terms of generating these embeddings. And there's very little evidence that these embeddings are worse than using OpenAI, for example. This is something you hear a lot, but I just haven't seen anything that proves it. So yeah, very cool Model-to-Vec models. They're like between 2 and 8 million parameters. Awesome. Okay, but like semantic chunking is tricky. There's so many decisions you want to make. You don't want to really be coding up these algorithms yourself. What's the solution to that? Well, one library that I really like is Chonky. Chonky is a great minimalistic chunking library that makes a lot of these decisions for you. It has very few dependencies, and it has a lot of different chunking options. It has a sentence chunker, it has a recursive chunker, it has a semantic chunker with lots of different params that you could choose, and it has like even a complex chunking algorithm called SDPM chunking. We'll get into that in a sec. So I mentioned previously that more complex semantic chunking algorithms exist, and the very bad news I have here is that these algorithms seem to be good. And this is bad news because seem is a very interesting word. We don't really have good chunking benchmarks at this point in time. It's very difficult to create a chunking benchmark because just if you really think about it, it's very difficult to figure out, okay, whether text segmentation is good or not. But there is evidence that some of these semantic chunking algorithms are better than others. And I'm just going to go over some options that you have just so you know that just so you have like some kind of taste for them. But I'm not going to necessarily say this algorithm is better than the other algorithm because I haven't seen defensive benchmarks that show it. So the first is cluster semantic chunking, and this is a very basic idea. Instead of just like checking if there is like some limit in chunking, segmenting at that place, what if we instead cluster together these like smaller chunks, segments, and then try to figure out, okay, let's make clusters, let's cluster them together. And there's many different ways you cluster chunks, but this seems to be effective. Another good strategy is cumulative semantic chunking, where instead of checking whether a chunk is different from the previous, whether a segment is previous from the different previous segment, you instead check whether it's previous to the accumulation of some of the previous segments. So this is just an optimization, and it seems to work well. Another is statistical chunking, and statistical chunking is, you can try with a library, Aurelio AI, and they have like a few of these different chunking methods, and they kind of pioneered a lot of them. And the advantage of this one is that it tries to compute the optimal similarity threshold dynamically. So this is what you can get into, like ML chunking here. The idea of like, okay, like you're trying to tune these hyperparameters for chunking and try to figure out automatically what the best hyperparameters are. Another is SDPM chunking. It's honestly a mess. It groups similar sentences. It skips over gaps to merge related parts, and then splits them into well-sized chunks. Now, if reading this doesn't make any sense, that's because I don't really get the algorithm. I tried reading the code for it, but it kind of went over my head. There's no evidence that this performs better than something like statistical chunking, for example, that I've seen. So that is very strong. But it's something to consider. You could try very easily with a chunky library. Okay, so the chunky library is just like, it's fast, it's simple, it has a really great API, and one thing to remember is the context of this library. This library is built in the context of most people who are doing chunking are using very bloated, massive libraries like Llama Index and LangChain. And these libraries are terrible to use, honestly. From a DX perspective, for chunking, you don't want a massive library to do a very specific task like this in many cases, right? They have the advantage of have these connections to like vector databases and like embedding models and all this stuff. But often as an AI engineer, it's easier for us to have like very specialized libraries that do exactly what we want, that are minimalistic. And these end up being faster and easier in many cases. So that's why I, as like a person who does a lot of AI engineering, like chunky. So, and it's also faster than these libraries. So chunky includes model to vec as an option, super simple DX, very few dependencies. It's very fast. It has almost 3,000 GitHub stars, and it has very little bloat. And another advantage is that I was the second contributor. So when you use chunky, you help me as a GitHub open source contributor. So that's fun. All right, so why does chunking matter in the first place? Well, this slide was supposed to be at the beginning of the presentation. So we can still cover it, I guess. I just put it in the wrong place. Well, RAG pipelines typically need some text for context. We have all these chunks. We want to retrieve just the relevant data that we need. And then we want to answer a user question. Or we want to just do simple retrieval. We don't necessarily have to do retrieval augmented generation. And it's very important that our chunks are coherent. And there's two different things that we need for chunks generally. One is that when we pass the chunk to the LLM, the chunk needs to make sense. If the chunk is missing some context, well, the LLM might hallucinate or make something up or create context that doesn't really exist. The other is that the chunk needs to be relevant to the question in the first place. That's why we need the chunk to make sense when we embed it and put it into embedding space with embedding model. So two large chunks can dilute relevance, and two small chunks can completely fragment our context. But there's only so much that chunking can do, which is why strategies like contextual chunking make sense that add context to that specific chunk. This not only adds the context that the LLM might need, but it also changes the location of the chunk in embedding space, which could potentially improve retrievals. Another fun thing to note is, let's say we're trying to segment text into sentences. So previously when we talked about semantic chunking, I actually don't know how well I'm using this microphone. I feel like I'm going back and forth, but I'm doing my best. Okay, this is good right now. All right, I'm gonna keep it this close to my mouth. So previously when we talked about semantic chunking, we spoke about these smaller parts that we're trying to merge. That's the whole idea of semantic chunking. But how do we actually generate these smaller parts? Well, one way is we could find these delimiters and try to split on those delimiters. These delimiters might be an exclamation point, a question mark, a period, and split on those delimiters. But a very good option is PySBD, which is kind of like merged with the Spacey library. And it's just very effective at breaking text into small sentence-sized chunks. So here we have an example where it says, my name is Jonas E. Smith, please turn to page 55. And it correctly chunks this into, my name is Jonas E. Smith, and then please turn to page 55. Doing this yourself would be very challenging. And it's also very, 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 very fast compared to other options. So I think it's really cool. Okay. Now, it's 2025, right? We've seen this before. we've seen semantic chunking. This is old news, right? You're like, we're at a chunking meetup. Like, we expect some juicy stuff, all right? And here it is right now. Agentic chunking, all right? We tried everything. We tried everything. We tried semantic chunking, didn't give us good results. We tried all these other chunking options. We need something that is as good as a human at this point. And that's where we have agentic chunking. We either have a human manually parsing these documents and figuring out where we're splitting them, or we could use an LLM, which is in many cases just as good. So an advantage is that it's intuitive, it's context aware, it understands our entire document, it can handle complex or unstructured text, and I personally think it's cool. So if you use it, talk to me, I want to see your results. So that's a bonus. Cons are that it's expensive, not mainstream, not a lot of documentation on how best to use this, not a lot of best practices, and it requires careful prompt and design. So in Nina's unstructured example, we found that a small prompt tweak actually improved our results. So that's the kind of situation you're working with when you're using something like agentic chunking, where you as an engineer might think only in code, but here a prompt tweak might be the difference between a success or a non-successful chunking strategy. So the most common LLM chunking strategy, and it's not very common at all, is LLM merge chunking. So this kind of new terminology that you kind of like have to make up at this point in time, but this is very similar to how semantic chunking works. So what we do for LLM merge chunking is we segment text into sentences, say like with something like PySPD, and then we insert artificial delimiters so that an LLM knows, okay, when does each one of these segments start and end? And once you tag each sentence with chunk markers, you send it to an LLM, which makes a merge decision. And the LLM then identifies merge points, and it extracts merge indices, and then it merges these sentences into chunks. So what comes out is almost a human-level chunked output. Right? This can have many errors. The LLM could hallucinate. It could get like its numbers mixed up. There's so many things that could go wrong. But in theory, this should give you a chunking output that is very similar to that of human. So how do we actually do this in practice? Well, let's zoom into the code of how to do it. There are a few steps. First, we segment the text. I don't know how well you could see. Then we merge indices with the LLM, and then we get the merged chunks. So our prompt looks a little bit like this. You're an assistant specialized in merging text into thematically consistent sections. You must respond only with IDs of the chunks where you believe a merge should occur. You must respond with at least one merge. Right? And then you could use that to programmatically create very high quality chunks that look like this. But this is all up in the air. There aren't really libraries that do this well at this point, I think. If that's something that you're interested in, please let me know. I'd love to chat with you, just because I think this is really cool. And often when people have really complex or important chunking decisions, this is probably what they turn to. Okay, so there's not a lot of chunking research. None of this presentation actually told you, okay, what's the best chunking strategy based on any kind of actual hard numbers? Well, Chroma actually did some research on this. And they did this in a very clever way. I'm not going to go into how they very cleverly found out or measured how well different chunking algorithms work. But the hard part was really creating this data set. So they created a very high quality data set, and they were able to measure the recall precision and something they called the IOU, which I don't want to get into, but it's like kind of like, you can think of it as the accuracy kind of, although don't quote me there, of how well these different chunking strategies work. And what they found is, in general, a good heuristic is if hyperparameters are set well, then boundary-based strategies are good. They're fast, they're easy, they're good. Semantic is typically a bit better, and it really works, with complex algorithms proving to be like sometimes a little better. And then also LLMs are extremely good out of the box, where you don't really have to set these hyperparameters because they're just great. And they have like a very naive prompt, and there's a lot of improvements that likely can be made. So with LLMs. So this is basically a good heuristic to have when you're making a decision. But another thing you get from the study is that evaluation on chunking is very, very, very challenging. You're not going to be able to build your own benchmarks in many cases. It's very, very good if you're able to, but it's very challenging too. So a lot of the way people will kind of figure out whether a chunking strategy is good at this point in time is looking manually at chunks and figuring out whether they're good. And that's just the reality. There's no really better way at this point. Okay, another fun thing is, let's say you are in a position where you're doing PDF parsing with chunking. Well, there's many platforms that do this, and what they do is like very complex. Like they don't just use an LLM to parse the document. There's a lot of steps that go into it that Nina mentioned, and we're going to see later as well. But if you want a quick, easy, and cheap solution, LLMs can do all of this in one step. They could parse a document and they could chunk it into sections, right? Will you get the best possible outcome? Probably not. But can you like create a quick demo or even get potentially really good results for extremely cheap? Yeah, Gemini is super cheap. It could parse your results. It could turn it into chunks. It could do a lot of that. And whether you use this or not, or you use a more complex option like unstructured or chunker, it's something that you need to understand to kind of like know, okay, like how do these like tools kind of work? All right, so like let's say you were like trying to build your own PDF parsing and chunking strategy from scratch. Again, this is extremely naive and this is not enterprise ready. Well, what you would do is you would take a PDF, you would turn it into an image, you would pass it to a VLM or Vision LLM like Gemini Flash, and then you ask it to give you not like individual chunks. And then you embed these chunks, you could put it into a vector database like KDBI, and you do query and RAG. Now, the last step you could actually do with any of these platforms. Like KDBI actually has an integration with unstructured, so you're able to not only get the individual chunks from unstructured, but you could also get a lot of the metadata about the documents, which can then help you when you're searching later. So a lot of the times when you're searching with vector databases, you want to be able to use metadata filters. One, because they'll speed up your search. And two, that can make your search a lot more precise because you're weeding out these irrelevant documents. Okay, bonus round. I swear I'm almost done. Late chunking. You might have heard late chunking around, and what is it? Late chunking is this idea that when you're generating an embedding, instead of taking the individual chunks and putting it into an embedding model, what you're going to do is you're going to put the entire document, hopefully your document fits in this embedding model, and you're going to put it into an embedding model and you're going to get an embedding, and you pull around the edges of the chunks. So you look at where the boundaries of the chunks are, and then you pull the token embeddings, because the way embedding models work is they take individual token embeddings and they basically combine them together or pull them or average them out into an overall embedding for that thing that you put into the embedding model. So what we could do is if we like remember the boundaries of these individual chunks, we can get the embedding for the entire document, and then we could like only pull the embeddings for the tokens inside that chunk, but now they have the context of the entire document. So what we've done is we've done a transformation in embedding space towards the meaning of the document. So what you see in practice is that the embeddings are clustered. Well, this is something that typically improves retrieval, right? This is just like a strategy that improves the quality, improves the retrieval accuracy that you have in many cases. But it's also something you could use in chunking. Well, instead of using the embedding for the individual like segments and seeing if there's like a massive difference, you could use this transformation to see, okay, like let's use the late chunking embeddings of the segments and chunk on those instead, right? And Chunky actually supports this, which is really interesting. I was pleasantly surprised to find that they support this. Okay, bonus, contextual retrieval. You're already familiar with this from the previous presentation. contextual retrieval has a lot of bonuses. One, it fixes this issue that we don't really know the context of the entire document in our chunk. It also can move our embedding in a good place, towards a better place in embedding space. But even with something like contextual retrieval, it's typically still best practice to do something called hybrid search, where we mix keyword search with embedding search. And then when we do a query, we actually retrieve using both these strategies. And the advantage of this is that it improves recall. It improves the number of documents that are potentially relevant that we retrieve. And then we could re-rank later to get the most relevant documents into our to our user or to our LLM. So this is just best practice, and that's why KDBI puts a lot of focus on a hybrid search, and that's something we're trying to push, as this is best practice in today's world. Even if you're doing something like contextual retrieval, you still want to be doing hybrid search in almost all cases, just because it improves the accuracy of your retrievals. And what we saw before is that contextual embedding plus BM25 is probably the best way to reduce failed retrievals. But let's go farther. We had our LLM generate context for our chunks. Now let's generate some metadata and tags. We want to know what kind of document it is. We want to know the topic of this document. We want to know what users, what entities were included. We want to know what category it is. And especially that last part, then when we're doing retrievals, we could have an LLM generate the specific category or the specific metadata or the specific timestamp based on the user query, and then get a much faster and more accurate result. So metadata filtering ends up being extremely important. And that's why KDBI focuses on pre-filtering, where we first filter out all the relevant data and only search the relevant data, which massively improves latency in practice. Okay, all right, so you did chunking. You did all this like research on chunking. You have a bunch of chunks, and you're like, okay, like I want to search these chunks now. But you have a problem. You have too many chunks, and your existing solution, you're just paying too much. Well, at KDBI, we thought of a solution for this. So we saw that in practice, people were paying way too much for vector databases. So we did two things. One, we created the best free cloud tier for a vector database where you could get quite a lot of vectors in free. Like I got 5 million vectors in. These are small vectors, so I quantized them quite a lot. But I got it in like a few minutes. It was a really easy time, and you can go quite far with a free cloud tier. And the second solution was QHNSW, which is specific on-disk index. So what we found is that we could actually store these embeddings on disk instead of in memory. And not only is this like many orders of magnitude cheaper, but it increases the request per second that we're able to handle. Now, we were able to do this with a very small impact on latency. So if you're in a situation where you're paying too much for a vector database, on-disk indexes is usually the way to go to save on costs. Yeah, so this is like an example, like it's super simple to do this. And if you're like trying to get started with a vector database, I'll be happy to talk with you, see how much data you have, guide you through the journey, and like give you best practices on how to spend as little and have as good quality and like have the fastest retrieval possible as you can. And we have other indexes as well. We have like traditional HNSW indexes. We have flat, both on disk and in-memory flat indexes, which are very easy to work with, but aren't great in latency as you scale. And then we of course have IVF and IVF PQ, which turn out to be pretty good options when you get to a certain scale. And of course we have our unstructured integration. So that's the entire presentation. This event, once again, is brought to you by KDBI, which got us the pizzas and the venue and all the things and all the shirts and made this possible. And Cracked SF, which runs monthly meetups in San Francisco focusing on technical topics.